Now, the last thing that we need to look at in this lesson is isoclines. An isocline is just a line, and it could be a curve, could be a straight line, but it joins all of the points that have the same gradient in our slope field. So in our first two examples in the last video, our first example had y dash equals to half x. And remember, we didn't bother even drawing out the whole grid of all the gradients because we realized that all the rows were the same. Now, if all the rows are the same, then it actually didn't matter what the y value was because there was no y in this equation. And so what it meant that basically every single vertical line was an isocline, and we could draw them in by saying, hey, along this line, every single section or every single solution curve has got a gradient of 0. Along here, every single solution curve has a gradient of 1. Along here, every single solution curve has a gradient of -1, or so on. Actually, it's not. I've drawn different things there, and this is just a very, very rough sketch. But we can see that if the gradient is the same at all of these points here, then those lines that we can draw through those points that have the same gradient in their little line segment, those are all isoclines. And we could say that the line x equals 0, the y-axis here, is a special isocline because it's joining all of the turning points in the potential solution curves. In the second example, we had y dash plus x equals 0, and we found that all the solution curves were circles that have their center at the origin. So all of the isoclines in this example would be radii of the circle, or even diameters. So, for example, we could draw an isocline through there and say that in all of those points the gradient is exactly the same. We could even keep that coming all the way through. Sorry, a little bit of a dodgy line there. And in fact, all of the radii, no matter which one we pick, would be going through points that have the exact same gradient. Now, if you have isoclines that contain horizontal line segments, in other words, flat spots like this isocline did, then it shows you where the stationary points of the solution curves lie. For this one, it happened to be all the way down the y-axis, but for other differential equations and slope fields, it won't necessarily be that way. So they're a handy one to look out for. Now, some more really important points about isoclines. They can be horizontal lines when y dash has constants in it. So to just consider an example here, I think this makes sense. If y dash is equal to something like y squared minus 2, then as soon as you've got values of y squared that equal to, in other words, when y is equal to plus or minus root 2, you're going to have y dash equaling 0. So you're going to get line segments that are horizontal. So you'll get a row of those straight away as soon as y equals root 2 or minus root 2, and you could fill in that row as the first thing that you put onto your slope field. Now, this feature is going to help us to find constant solutions. What are those? Well, they're examples of the more general phenomenon, equilibrium solutions. Now, we're going to look at equilibrium solutions specifically in an example in a moment, so that will make a little bit more sense then, but for now, let's just highlight that as something important that we need to consider. Next important point is that if an isocline consists of line segments that have the same gradient as the isocline itself, then we can make some assumptions. We can say that that isocline actually is a solution curve, and that means that no other solution curve crosses it, because generally solution curves don't cross each other except for in unusual examples that we generally won't see in this course. Also, we can say that that line will divide the solution curves into two groups, because if none of the solution curves are crossing it, they're either on one side of it or the other, and that isocline may be an asymptote of the other solution curves. Now, to look at this example up here as a nice simple way of understanding these points, we can see here that we've got two lines that have a gradient of 0, so the isocline has a gradient of 0, and the line segments that it's made up of have also got a gradient of 0. So we've got two examples here, the line y equals root 2 and y equals minus root 2. Let's just examine this one. Is this actually a solution curve to this? Well, we sub it in. We could say the left-hand side over here would be y dash, and if I differentiate root 2 with respect to x, I just get 0. And if I look at the right-hand side, then we get y squared. Well, what's root 2 squared? It's 2 minus 2, which is also 0, so that's equal to the left-hand side. So sure enough, this is a solution curve. It's a really simple one. It's a horizontal line, but this is a solution to this differential equation. Now, will all of the solutions actually just be horizontal lines? No, they won't. But we've already seen that some solutions to differential equations will have completely different shapes. Now, Is it possible here that this isocline may be an asymptote of the other solution curves? Yes, because before I even investigate here what the other slopes will look like in and around here, if it's tending towards a slope that's horizontal, then we've potentially got lines that are sloping in towards this or away from it, or sloping in this way or that way, or sloping in here and here. So we've got an actual line that is a solution, and then we have other lines that might be tending towards it. So 2 examples will make all of this seem a lot clearer, I think. Now in this question we need to sketch possible solution curves, so we need to somehow thread our solution curves through this slope field. We're given the slope field and we're given the differential equation that's been used to create it. So sketching possible solution curves, well, we can make as many as we like, but if we're going along here saying, all right, well, we're pretty close to being a horizontal gradient here, then it's potentially tending towards one. We've probably got this line here, y equals 2, as an asymptote. So any curve going along here is going to tend to go shooting up at some point. So whether it's gone shooting up there, or perhaps it's gone along and then gone shooting up here, or perhaps, it might have gone along further before going shooting up there, we've got a variety of options. When we look at this section here between this asymptote and this one, and we can see they're asymptotes because we've got horizontal line segments there, we can see the gradient gets steeper and then it flattens out again. So we've potentially got solution curves that do something like this. But whether they do it here or they go along further before going down, we can see that they're tending to then flatten out. So each one of these, if we put some arrows on it, represents a completely different solution curve. These go up, these go down. Now underneath this horizontal line, we've got the same sort of thing. We could have a solution curve coming up and it's tending then to go towards a horizontal gradient. So whether it does that here or it comes along further before moving up, we've got solution curves that look something like that. All right, identify the constant solutions. Well, we could also have a solution curve that literally just went straight through. Let's do that in green. This is also a solution curve, and so is this. Now, the ones that we did in red were the curvy ones, but there's clearly some straight lines that are also perfectly good solutions. They go straight through those gradients there. So the constant solutions would be in green. Let's call those y equals 2 and y equals -2. All right, substitute the constant solutions into the differential equation to confirm that they actually are solutions. So this is what we did in the last exercise. We've done a lot of this so far. We need to start by saying, all right, the left-hand side is equal to y dash. Now, if we're choosing that y equals 2, then y dash would clearly be 0. And on the right-hand side, we have 1/4 of y minus 2, y plus 2. So if we're saying that y is equal to 2, then that's going to be it's not a half, it's a quarter. I said a quarter and I wrote down a half. Silly me. It's a quarter of, we've got 2 minus 2, which is 0, times 2 plus 2, which is 4. So clearly we're going to get 0 there, and that also equals the left-hand side. And we could do the exact same working using y equals -2, because differentiating that, we get 0, and here we would have 4 times 0, so we're going to get the exact same thing. So that's C, that's done. All right, here's where it gets interesting, and this is where we can start to understand the whole idea about equilibrium solutions. If the horizontal axis represented time, so instead of this being x, let's imagine that it was t, then describe the behavior of the solution curves, so all of these curvy ones here, how are they behaving near the constant solutions? Well, the constant solutions are the green ones, and clearly they're asymptotes to the other solution curves. So as time increases, in other words, as we move to the right, which of these two lines, y equals 2 and y equals -2, shows unstable or stable equilibrium? Okay, so here is the key point that we're looking at here, the stability of the equilibrium. Well, if we look at what's happening in and around this line here as time ticks along and we move to the right, the solution curves may well go along that, near that for a really long time, but at some point the slightest deviation is going to send them shooting up. And so that shows a very unstable equilibrium. They might be going along right on this line before then, or not on it, very close to it, before shooting up. So this one represents an unstable equilibrium as we move to the right. Whereas this line here represents quite a stable equilibrium, because it doesn't matter whether we're looking at the solution curves that are between here and here, or the solution curves that are below that line y equals -2. Either way, as we move along to the right and time ticks away, all of the solution curves, even if they start up here somewhere, at some point they're going to deviate down and end up really close to this line. And if they were down low, eventually as time ticks along, they're going to move up. And so that's increasing the equilibrium, it's increasing the stability, and we can say that this isocline here represents some sort of stable equilibrium as we move that way, because a lot of the solution curves are converging on it in a way that shows that it's an asymptote, but it's almost like it's drawing them in, if that kind of makes sense. And now our last example for this lesson. We need to sketch the slope field for the differential equation y dash equals x plus y. Now, this should be familiar because it's an example that we already looked at in exercise 13a. So this is a really good one to revisit. And now a whole lot of 13a should make a little bit more sense. Now, I'm going to cheat a little bit, and I've printed out here the table of gradients that we would make for this slope field. So come on in a little bit closer and let's have a look. Now, we're just adding x and y values together. So it's almost like a little addition table here. You can see straight away the zeros going all the way down, because when we've got -4 plus 4, we get 0, -3 plus 3 is 0, etc. We can also see that there's diagonal lines showing the isoclines here all the way down. Now, isoclines might be really nice and visible on your slope field, but there's a chance that they're going to be even easier to spot on your table. So that's one of the main purposes of these tables, is that we can see, and this is a question here, identify all the isoclines. Well, I can see that all of the isoclines occur like this, and that's going to correspond with all of the lines on our slope field that have a gradient of -1. So, sketch the slope field. Well, again, I'm going to cheat a little bit. Well, a lot, actually. Complete cheating. And we're going to have a look at one that's already been sketched. So, what we can see here is the same sketches that we actually made in the example in exercise 13a. Now, we can see straight away down this dotted line here that we've got horizontal line segments there, so that was equating to all of those gradients being 0, and all the way down here the gradient is 1, and all the way down here the gradient is whatever it was 2, and then 3, and then 4, and so they're all integer gradients actually. Now, why do we get this sort of shape, and what exactly is going on? Well, sketching some solution curves, this has already been done for us, but we can see here that because we've got all of these lines here, where you'll notice that the main feature of this special solution is the fact that the gradient of the line segments is the same as the gradient of the isocline itself. Let me say that again. Remember that an isocline is just a line that joins all the points of equal gradient, and I could make isoclines going all the way down here. All of the lines that have got a gradient of -1 are isoclines. But this is a special isocline because the gradient of the line segments is exactly the same as the gradient of the isocline itself. And so it is actually a solution curve. Now, it's not a curve really, it's a straight line, but it is a solution to this differential equation, and this might jog your memory. We saw this back in exercise 13a. All right, so sketching some solution curves, they're all on there, and we can see that they're all tending towards this line as x gets more and more negative, and then we can see that they're getting steeper and steeper. We could draw another one here ourselves by going down here and then threading our way through the slopes. Okay, we can draw in as many as we like. Out here, we could have others that are coming out this way, and there's lots and lots of solution curves there. Identify all the isoclines. Well, I would say there for that, let's just answer that question. C, it would be all lines with gradient -1. And so we can identify them because they're all parallel with this dotted line and also with the special isocline that has its line segments being parallel with itself, or the same gradient as it has. All right, D, explain the significance of the isoclines y equals minus x, that's the dotted line, and y equals minus x minus 1. Okay, so y equals minus x is the isocline that connects all of the points where the gradient is 0. So we could just say that it passes through all the turning points of the solution curves. We'll say all turning points of solution curves. And then the significance of y equals minus x minus 1 is that it is actually a solution curve itself. It is a solution curve. And it's also an asymptote of the other solution curves, of the other solutions. Now for the last part, we need to show that y equals a e to the x minus 1 is a solution. Now in exercise 13a, we were given this and we were asked to differentiate it to check that this was a solution of this differential equation. So we've actually completed this check before, but we'll do it again now that we are considering some other things here, and we can see how the sketch of the slope field really helps us, because in exercise 13 we had to sketch the possible solution curves for this, and that was quite tricky. And I think now that we've got this new skill, it makes that 13e stuff a lot easier. So if I just leave that there and I can work underneath here, then subbing in the left hand side of the differential equation is y dash. So if our y is this, then differentiating with respect to x, we get a e to the x minus 1. Whereas the right hand side of the differential equation is x plus y, and that gives us x plus all of this is y, isn't it? So we need to add that all on. And obviously we've got x and we've got minus x, they cancel each other out, and we have a e to the x minus 1, which is equal to the left hand side. Or we could finish by saying, therefore, right hand side equals left hand side. The way you finish it is up to you. So we've shown that this is a solution. And when we looked at this in the last exercise, we looked at the actual equation of this and we reasoned why we were getting such different solutions that now appears a little bit more obvious. So we can see that when a equals 0, it's actually not going to give us a solution curve that's an exponential at all, because this whole term will disappear and we just get the line y equals minus x minus 1, which is this asymptote to all the other solution curves. Whereas when a is positive, we end up with solution curves that are above that asymptote, and when a is negative, they end up being below, and that really changes the nature of the curves. These ones that are above all have turning points that are sitting on this line, and the ones that are below are always concave down and don't ever have any turning points. And we can see now that we know that this is the general form of our solution curves, we can see why we get an asymptote along this line. And that's because as x approaches negative infinity, this term here is going to have y equals a e to the minus infinity, and what that really is a over e to the infinity. Now, a massive number on the denominator there, like e to the power of something huge tending towards infinity, makes this fraction virtually 0, no matter what value a has. And that means we essentially, as a heads this way, we lose that term, and what we end up with is just our minus x minus 1, which is why all of the solution curves are approaching that isocline there.